Aloha! This is lesson 7.5. We're going to talk about proportional segments and how they relate to parallel lines in triangles and not in triangles. So why don't you take a moment and try to do this proof, right? So pause and then unpause when you're done. All right, so let's look at what we're given. So we're given this triangle with parallel sides, and we're trying to prove these two triangles, a smaller one and a larger one, that they overlap, that they are similar. So because of that, I know I have three possible conjectures to prove them congruent, theorems or postulates. And let's start with our given, which I'm sure is what you started with. Okay, where segment PQ is parallel to segment RT. And 2. All right, so what do we know about parallel lines? Well, parallel lines proves angles congruent. So I know that this is congruent to this. Angle 1 is congruent to angle 2 because corresponding angle postulate. And then this would also be for the same reason. Now you could have grouped, since you're using the same reason, you could have grouped line 2 and 3 together if you wanted to, and only used one line. And that could have been just line 2. Now, you may say, Ms. Mendez, that's not what I did. I did one of those pairs, but I used angle PSQ is congruent to RST. And I'd be like, it's great. What's your reason? Reflects the property of congruence. Lovely. And that's fine too. Since we only need two angles, that's enough. So whatever way you did it, as long as you can prove two angles congruent, you're good. So because I have that, I know I can use angle. So the two triangles are similar. Okay, from angle, similar. All right. So remember that when we do similarity, it says that the angles are congruent and the sides are proportional. So now we're taking that and we're extending it. And this is called the parallel proportionality conjecture. At least this is what your book calls it. In other textbooks, it's a triangle proportionality theorem. It's C64 in your book, so you know. But like I said, different. So if you wanted to look it up online or on the internet, it may be under triangle proportionality theorem and what it says. So if I have a line parallel to one side of a triangle and intersects the other two sides. So in that, they're talking about PQ. So we know it's parallel. We know it intersects the two sides. So it's intersecting SR and side ST. Okay, so if that happens, then it divides it proportionally. So we don't know if they're congruent, right? Clearly it's not, but we know that this part is proportional. So you can say this to here, to here, to here, right? Is what I wrote in there. Right. And then firstly, so if a line divides the two sides of a triangle proportionally, so this time, if I know they're proportional, right? Then the line is parallel to the third side. So this is if it's parallel, then you know the sides are, it's broken into proportional parts. And then here, if you have proportional parts, again, in a triangle, then you know the lines are parallel. So why don't you take a moment and do these two problems applying what we had. Ooh, I forgot a variable on this one. My bad, I'm just going to put it right here. Find that. All right, so we can see that these sides are parallel. Using the theorem, it says that it's proportional. So the pieces, so 18 over x equals 24 over 20. Okay, and then we're going to cross multiply. And it is 15. Okay, this one we have 2. So we know that from here to here and here to here, we can say they're proportional in x to 15. Again, cross multiplying. Now what about y? Can I say 3 to y, 9 to 12? No. This time, because you have that part, right? This third side, that parallel side, is not being cut up at all. So you're going to need the whole thing. And so again, I think that was 3. I just wrote over it. There it is. Okay, so we're going to say to find y, it is 3 to 3 plus 9, right, which is 12. And then y to 12. Oh, so what does that tell us? Well, it looks like y equals 3. Right? There you are. Next. So this theorem is, what if you extend it? What if you have more than one line that is parallel to the third? What if you have 2 or 3 or 4 or 5 or 6 or 7? Well, then it is all proportional. So, give me a moment. Okay, I may forget one ratio because there's a lot. You can say A to B to E to F, right? Which is also which we could say is proportional to B to C. Sorry, that's not right. That'll be confusing. I'll just write it this way. B to C is F to G. C to D is G to H. But you can also say A to D is from E to H. Oops. Sorry, I said H. I wrote F. And there's more, right? There are. But we're just saying they're proportional on the left to the right. But they have to be together this way. They have to stay this pair together, right? Okay, so we're looking at here. Oh, I did want to say I have never seen this theorem in a different book, just so you know. But it's really just an extension of the other one. They use a different theorem, which I will talk about after this problem. Okay, so we're looking here. Remember how I told you you have to straight across. So this one, that has a variable. This one has variable. This is not, so I can use this. And then these go together. So I'm going to do 6 to 8. It goes to 8 to 6. So it's 8, 8, 36. Okay, which I'm going to simplify that to 9 halves, right? So 4.5. And I'm going to use 6, 8. And I'm going to use this for 3 over b. And this, cross multiply. Okay. And then we're going to do the last one. 7.5 over c. I don't know what that is. I'm going to use my candy dandy calculator. 60, that is oops, sorry. Got carried away in my letter writing. Is 10. Now this one is called proportional parts of parallel lines theorem. This is actually the theorem that is more used in textbooks because you don't see triangle. And this gives you more freedom in doing it because you may find things that are parallel, but that aren't necessarily in a triangle. And the reason why this theorem works is because of the other theorem, because I could extend this and it would be a triangle, right? But you don't need the triangle. So this is why this theorem's a little bit more versatile. So it says if you have two or more lines parallel to intersecting transversal, so our transversals are, are here, so that's one, and then here. Then they divide the transversal proportionally. Okay, so DE is on this side, then EF is over here, and then AB is here, and BC is there. All right, so solve the variables here. Eight. And there you are. Now this, you can see it is very similar to number 3, that you have the multiple lines, right? And so these just all go together. So the ratio that we're going to be using is 3 to 2. And I know some of you could probably just do these in your head, seeing the relationship. But sometimes it's good to show your work so you don't make a mistake. Another 4.5. And there you are. Okay. All right. Thank you for watching. Bye.